HLAA, Probability and Statistics, day number 3. Topics for today are probabilities by way of combinatorics, Venn diagrams, some circular probability, as well as the idea of mutually exclusive and independent events. Let's get started. So this basic idea of probability is as follows. The probability of event A occurring is as follows. Probability of event A occurring is n of A over n of t, where n of A represents the number of possible outcomes of A, and n of t represents the number of total outcomes possible, including A. Our probability in any case will always land between 0 and 1 inclusive. So let's look at an example. A committee of 4 people is selected from 7 men and 6 women. How many different ways can each of the following be done? Now, there are no specifics on positions within the committee. So if you're selected to the committee, you're just a member of the committee. You're not the president or the vice president or anything like that. Therefore, in this case, we would use a combination. Okay, if there were to be specifically defined positions, that would be a permutation. So if there are no restrictions on the 4 people selected based on male or female, the answer to this question, right, the probability, actually I guess this problem isn't asking for probability, it's just asking for the number of ways something could be done. So the number of ways to choose 4 people from a group of 13 would be 13 choose 4. Now, I would encourage you to get comfortable with your calculator. Of course, this would be algebraically equivalent to 13 factorial over 9 factorial, 4 factorial. However, with your calculator, you can simply press the math button, go over to the probability tab, and find NCR. Plugging in a 13 for N and a 4 for R, you get 715 possibilities. Okay, part B, an equal number of men and women. Now, this is going to be an example of the multiplication rule, right? If we were to choose, as we talked about in past lessons, 3 items out of some group, we have 3 possible selections out of one group, but we got to choose one, right? Our smoothie example, if you will. Right? In this case, we're going to be choosing 2 males, and the way to choose, or the number of ways to choose 2 males, followed by the number of ways to choose 2 females, would be 7 choose 2 times 6 choose 2. Okay, using your calculator, press math, go over to the probability tab, and select option number 3. So that'll be 7 choose 2 times 6 choose 2, which comes out to be 315 different ways. Okay, now for part C, slightly different, we're going to find the sum of 3 possible scenarios. Actually, I suppose it's, well, let's look at it. So we could find the number of ways to select 1 female, 2 females, which we've already done, and 3 females, and finally all females. All right, if we found the number of ways to choose 1 female, 2 females, 3 females, 4 females, if we added those up, then we would have what we're looking for here, which is at least 1 female selected into this group. So let's highlight these by color, understanding that we've already found our blue value right here. Okay, so this would be 7, number of males chosen would be 7C3 times, that would be 6C1. That would get us our red answer. Our blue answer we already know, 315. Our green answer is going to be 7C1 times 6C3. And our yellow answer will be 7C0, which will be 1, times 6C4. All right, I'll come back with an answer here in just a moment. All right, so when I do my calculation here, the number of ways to choose 3 males and 1 female is 210. We already knew the 315 for 2 of each. Calculated 1 male, 3 females. And just so you know, if you ever do a number choose 1, or a number choose all of those, so 7C7, there's always only 7 ways to do that. Okay, so our green answer here comes out to be 140, so that's 7 times 20. 6C3 is 20, plus 7C0. 7C0 is 1 times 6 choose 4, which is 15. So the total number of ways to select at least 1 woman is 680 ways. There you have it. All right, let's look at some probability. We've used these to find the number of ways to select. This is a combination method, right? Let's now look at some probabilities involved. Okay, so here's an example. A family has 3 children. List the sample space for number of boys and girls possible. Then calculate the following probabilities. Okay, so the first question here, question A, is asking the probability that you have 3 boys. Okay, the second is asking probability that you have 2 boys and 1 girl. The third probability is asking for the probability that you have at least 2 girls, so either 2 or 3 girls. So let's create the sample space. So first child is born. First child is either a boy or it's a girl. Second child is born. Okay, and then third child is born. Now, this looks like 8 children being born here at this last step. It's not. It is the possible stems throughout. So, for example, let me show you. Let's say one option is boy, boy, boy. The next option on that same branch is boy, boy, girl. And so on and so forth. Our next stem would be boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Oops, girl, boy, girl. Girl, girl, boy. And girl, girl, girl. So let's answer our question for part A. Probability that there are 3 boys born to this family of 3. Well, the probability of that would be the number of ways that 3 boys could be born over the number of total, which in this case would be 1 out of 8. Okay, part B, probability that there are 2 boys and 1 girl born. Okay, so I'm going to star this, and we're going to mark in our sample space all scenarios where there's 2 boys and 1 girl. 2 boys, 1 girl, 2 boys, 1 girl, and 2 boys, 1 girl. All right, that looks like the number of ways to have 2 boys and 1 girl is 3 out of the total number of ways to have 3 children, which is 8. Okay, now we want to work with, yet again, another summation of different probabilities. So the probability that there are at least 2 girls is the probability that there are 2 girls, plus the probability that there are 3 girls. So let's use yellow here. Okay, so I'm going to star any that have 2 girls, 2 girls, 2 girls, 2 girls, and then any that have 3 girls. So the probability that there are greater than or equal to 2 girls in this family of 3 would be 4 out of 8, or 1/2. Outstanding. Let's continue with another example. All right, let's get into a Venn diagram probability here. So consider the Venn diagram scenario, draw the sample space, and find each of the probabilities given. For events A and B, the following are true. Probability of A is 0.6, probability of B is 0.7, and the probability of A or B is 0.9. So let's go ahead and draw this sample space. And I'm going to draw the sample space with a rectangle and 2 circles. Here is the space which represents event A. Here is the space that represents event B. Now I know the space inside of event A is 0.6 or 60% chance of happening. The space within event B is 0.7 or 70% chance of occurrence. So anything outside of A and B, apparently, according to this data, is 0.1, right? And I can tell that because the probability of A or B is 0.9. So the sum of the space within A or B, as well as the space shared, is 0.9. Now, by definition, the probability of A or B is the probability of A plus the probability of B minus the area in between. Because when I take the probability of A plus the probability of B, I have counted the probability of both of them twice, so I got to take it away once. All right, so probability of A or B is 0.9, probability of A is 0.6, probability of B is 0.7. I can find the probability of both occurring at the exact same time. Okay, I'm going to take 1.3, subtract it away. I'm going to get 0.4 is equal to the probability of A and B. That assists me in doing a number of things. First of all, answering this first portion of the question. So the probability of event A and B happening at the same time is 0.4. Now I can do a little bit of math in order to find the portions of A that's not shared with B. And I'm going to do that before I answer any of my other questions. That'll be 0.2, because that 0.2 plus that 0.4 gives me a 0.6. Likewise over here, I'll get a 0.3. Now you can always check yourself here. 0.3, 0.4, 0.2, and 0.1. Does that add up to 1? It does. So now we can go about finding the other probabilities. Let's look at part B. Probability of A or B, not that, right? So this symbol right here represents the complement of. So if I were to find the probability of A or B plus this probability that we're looking at here, they should equal 1. Well, I know this is 0.9. I know this is 1. So this value, as we already know, is 0.1. Oops, 0.1. Okay, let's look at the next probability. This is the probability of A and not B. So this is the space shared by A and not B. The space shared by A and not B is this space represented right here by 0.2. Okay, now we haven't found this space yet, or this probability, so let's talk about that. The probability of not A or B. Okay, so not A or B. What I'm going to do is going to find the probability of not A and add it to the probability of B. However, there will be some overlap, and that overlap is going to be the probability of not A and B, which we already know. We already know this value to be 0.3. That's the probability over here. So I don't want to count it twice. I'm not gonna. So the probability of not A is 1 minus 0.6, which will be 0.4. Plus the probability of B is 0.7 minus 0.3. So we're going to get, what would that be? 0.8, I believe. So the probability of not A or B will end up equaling 0.8. All right, let's continue with another example. Okay, the idea of circular probability comes up in this example. I'd like to talk about that. So this question is going to differ entirely from that of a linear probability, and I'll explain in a moment here. So 3 girls and 3 boys sit at a round table. Okay, let me use letters for those boys and girls. Okay, A, B, C, D, E, and F. There's our round table. It's going to be very different than a linear orientation. How many different ways could the students or kids sit at this table? It'd just be 6 factorial, right? 6 different people could sit in seat A, followed by 5, followed by 4, followed by 3, followed by 2, followed by 1. So that'd be 6 times 5 times 4 times 3 times 2 times 1. Okay, 6 factorial, 720, I believe, 720. However, in a circular situation, you'd like to think that 6 factorial applies. Well, it doesn't. We're actually going to take, in the circular nature, 6 factorial and divide by 6. And the reason why is because if everyone moved 1 seat to their left, they would still be oriented in exactly the same way. And you could do that 1, 2, 3, 4, 5, 6 different ways. So regardless of how many rotations have been done, the seating arrangement would still be exactly the same. So what we're going to do is we're going to have 5 factorial ways for said students or people to sit at a table. This will always be true if you have circular nature to your seating arrangement. You'll take the number of seats factorial over the number of seats. And so you'll get this property. Therefore, we would have 120 different ways for the students to sit at a circular table. Okay, so now let's look at a probability. What is the probability that Tommy and Tina sit next to each other? Okay, so I shouldn't have put Tommy and Tina, but let's say Tommy is A and Tina is B. Okay, here's our table. Now these two are locked together. Right, now we are not seating 6 people because they sit next to each other. We're going to be seating 5 people. Okay, and we're going to take 5 factorial and divide it by 5. That'll give us 4 factorial. However, there's 2 different ways for Tina and Tommy to sit next to each other. There's 2 factorial ways. So we're actually going to take this item, this idea, and multiply it by 2 factorial. So there are 24 times 2, 48 different ways that Tommy and Tina can sit next to each other. Now that's the number of ways they can sit next to each other. The total number of ways we actually found in the previous problem, which was 120. There's 120 different ways that 6 students can sit next to each other in a circular fashion. Thus, the probability in this case that Tommy and Tina sit next to each other, this is not mathematical notation, but I'm just going to say that Tommy and Tina get sit next to each other. It's going to be 48 over 120, which will reduce, if you want to reduce or if you're prompted to reduce, what goes into both of those? How about a 12, which would be 4/10, which could reduce to 2/5. So the probability that Tommy and Tina sit next to each other is 40%. Okay, let's talk mutually exclusive and independent events. Okay, two events are mutually exclusive if the two events cannot occur at the same time. An example of that is, say I've got a deck of 52 cards, and event A is drawing a king of spades, and event B is drawing a queen of hearts. If I pull one card out of the deck, I can't pull both at the same time. Those are mutually exclusive events. Mathematically speaking, that means that if two events are mutually exclusive, that the probability of A or B, right, which is the probability of event A or event B happening, would be the probability of event A plus the probability of event B. And the reason why, we talked about the definition of probability of A or B earlier, which would be probability of A plus probability of B minus the probability of both. Well, mutually exclusive events imply that this is true, right? The probability of both happening at the same time is 0. Right, you can see that right here. Okay, so this right here, if you ever see mutually exclusive mentioned in a problem, you should use that property. Now, independent events, slightly different. Two events are independent if the occurrence of one does not change the occurrence of the second. So an example, two cards are drawn from a deck at one time, or one at a time, excuse me. Event A is drawing a heart from a deck. Event B is drawing an ace. Events A and B are independent if the first card drawn is a heart and is replaced back into the deck. So let's talk about replacement as opposed to no replacement. Here's my deck of cards. Pretty aggressively tall deck of 52 cards. Okay, I pull the card, and guess what? It's a heart. Okay, so I pull a heart. The probability of pulling that heart on the first draw would be 1 out of 4, right? There's 13 hearts, 52 total cards. Probability of pulling a heart is 1/4. If I replace it back into the deck, then the probability of pulling what was my second event? An ace is 4 out of 52. Okay, if I do not replace, no replacement, then the probability of pulling an ace now is 4 out of 51. So in this case, if there is no replacement, then the probability of an ace has changed. Right? It went from 52 cards down to 40 or 51 cards. But if there is replacement, then the probability of pulling an ace is exactly what you'd expect it to be. Right? It is unchanged. Therefore, this situation here, right, replacement implies independent events. Okay, now, independent events won't always have the word replacement involved. You have to consider the scenario, the criteria, and then determine independent or not. Now, there is a property for independence, and the property for independence is that if events A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Okay, so beware of that property. You might see that coming up in the future. All right, let's move on to our last example for the notes. All right, exam style question here. Consider two events A and B such that the probability of A is equal to the probability of not A and B, which is equal to 0.4, and the probability of A and B is 0.1. So let's draw a Venn diagram and determine the probability of A or B. So let's draw this out. All right, here's event A. Here's event B. I've got the probability of A and B. Let's highlight it. It's 0.1. Spacer here is 0.1. It's probability of A and B. Probability of not A and B actually will, this is interesting, graphically, will look like this. This is outside of A, but inside of B. And that's going to be this. Oops, 0.4. Now, we know that the probability of A is also 0.4, so that makes this space right here 0.3. 0.3. Okay, so let's find the probability of A or B. So for part A, probability of A or B will be the summation, or the sum of those three spaces, which should be 0.8. 0.3 plus 0.1 plus 0.4. All right, part B says show that events A and B are not independent. Okay, so we can do this in a couple of different ways. We can show that the probability, it says show they are not independent. So let's find the probability of A and B, which we know is 0.1. Now if A and B are independent, then probability of A and B should be equal to the probability of A times the probability of B. Let's show that that's not true. All right, probability of A we know is 0.4. Probability of B, we can see from our graph here, our Venn, is 0.5. Therefore, the probability of A and B would equal 0.4 times 0.5, which equals 0.2. Since 0.2 is not equal to 0.1, right, then probability of A times the probability of B is not equal to the probability of A and B. Therefore, A and B are not independent events. There you have it, guys. That's lesson 3. We will see you in the next video. Have a great day.